Comets, mysterious travelers crossing the universe, once feared by humans and once worshipped as omens of change. But behind that enchanting beauty are untold stories about the origin of the solar system and even life on Earth. In today's journey, we will explore a mission unprecedented in human history, launching a spacecraft to crash straight into a comet to decode its secrets. Make sure you watch until the end of the video because these discoveries may change the way we see our own place in the universe. And don't forget to subscribe to the channel to join us on the next journeys. As humanity entered the end of the 20th century, our understanding of comets was still as obscure as the mist covering the universe. Although as many as 8 spacecraft had been launched to approach these wandering visitors, most missions only stopped at fleeting glimpses. The most resounding success came in 1986 when 5 international probes simultaneously flew past Halley's Comet. The close-up images revealed a dark core covered in dust and vapor, which shocked the scientific community. Yet that contact was like peering through a narrow doorway. What lay inside remained a mystery. In the following decade, only 2 more comets were studied directly, Giacobini-Zinner in 1985 and Griggs-Schellerup in 1992. A few clearer images, a bit of space dust collected, all fascinating, but not enough to solve the biggest questions. What are comets made of? Is their outer shell loose ice or a solid block? And most importantly, do they preserve traces of primordial compounds inside, clues to the origin of life in the solar system? NASA scientists understood that observing from afar would never be enough. To delve deeper into the internal structure, they needed a stronger method, a direct impact. The initial idea sounded bold to the point of being unbelievable. Build a spacecraft not just to observe, but to crash straight into a comet. A controlled explosion, creating an artificial impact crater, would help reveal layers of material that had never been exposed to sunlight for billions of years. This plan, after much debate, was finally approved in 1999. A budget of $330 million was passed, and the project was named Deep Impact. The coincidence with the famous film released in 1998 made many think NASA had deliberately borrowed the name. In the film, humanity desperately launched a nuclear warhead spacecraft to stop a giant asteroid from crashing into Earth. In reality, NASA's Deep Impact was not meant to save the world, but to decode mysteries. Though the objectives differed, the common ground was that both emphasized the power and boldness of science when facing cosmic dangers and unknowns. The target of the project was Comet Tempel 1, a short-period comet orbiting the Sun every 5.5 years. With a nucleus about 8 kilometers long and 5 kilometers wide, Tempel 1 was not too large, but it was an ideal candidate. Its orbit was close enough to reach while posing no danger to Earth. This was the perfect natural laboratory to conduct a cosmic-scale experiment. Scientists were not at all certain what would happen when the spacecraft struck. Some hypotheses suggested that the comet's surface was only a layer of dust and porous ice, like a snow pile, so the object might pass through without leaving a distinct crater. Others believed there was a crust as hard as rock, and the impact would create a huge crater. Whatever the scenario, each contained valuable information. It would reveal how comets are structured, thereby illuminating the history of the solar system's formation. To carry out the plan, NASA designed 2 main components, a mothership carrying observation instruments and an impactor weighing over 350 kilograms, equivalent to the explosive power of about 5 tons of TNT. That figure might sound enormous on Earth, but compared to a celestial body several kilometers long, it was nothing more than throwing a pebble at an iceberg. The goal was not destruction, but simply to carve a mark large enough for science to read. The impact was expected to occur at a velocity of about 10 kilometers per second, 30 times faster than a rifle bullet. At this speed, the energy released would equal a large explosion capable of cutting into the comet's primordial material. Immediately after the event, the mothership would take images, measure reflected light, analyze gases and dust ejected from the crater. Each fragment of data collected would help assemble a more complete picture of the nature of comets. What made Deep Impact special was not only the technology, but also the spirit of daring risk. No one could guarantee beforehand that the mission would succeed. Would the impactor actually hit the target? Would the dust cloud blind the observation instruments? Or worse, would the impact leave no visible trace at all? All were lingering questions before the spacecraft was launched. However, that is also the beauty of science, accepting risks in exchange for knowledge. Deep Impact was not only a mission of exploration, but also a testament to how humanity dares to wager on the unknown, just to take one more step in understanding the vast universe. And this very step opened a new chapter in comet research history, bringing us closer to the greatest question of all. Do those tiny, icy, dusty bodies hold the secrets of primordial life? When the idea of crashing straight into a comet was officially approved, the entire Deep Impact project entered a phase of urgent preparation. The scientists knew that to turn ambition into reality, they needed a machine that was powerful, intelligent, and resilient enough to survive a journey of hundreds of millions of kilometers. And so, the Deep Impact spacecraft was designed in two separate parts: the flyby spacecraft and the impactor. The flyby spacecraft was the mobile observation station, weighing over 600 kilograms, about 3 meters long, equipped with giant solar panels to sustain its power. It carried sophisticated scientific instruments, most notably two cameras, one with ultra-high resolution and one with medium resolution to aid navigation. These electronic eyes would capture the historic moment when the impactor struck the comet, while also analyzing data on dust, gas, and emitted light. In addition, the spacecraft was fitted with a debris shield to protect against the risk of cosmic dust impacts. The impactor, the main character of the event, was more compact, weighing only 372 kilograms. Yet inside its modest shell was a combination of autonomous navigation technology and its own camera, called the Impact Targeting Sensor. This was the final eye, functioning up until the fateful second. Throughout the journey, the impactor continuously took images and transmitted data to the flyby spacecraft, which then relayed them to Earth. In other words, the last images humanity saw before the collision were the travel diary of this self-destructing device. NASA also cleverly used the mission to engage the public. In 2003, they launched a campaign calling on people worldwide to send their names. As a result, more than 625,000 names were etched onto a CD and placed inside the impactor. Those names, along with the metal block, truly touched the surface of Temple 1 in 2005, making Deep Impact not only a scientific experiment, but also a message from humanity sent into the cosmos. Another interesting detail: the chosen impact date was July 4, 2005, coinciding with US Independence Day. Scientifically, the choice made sense. It was the time when Temple 1 was closest to the sun, meaning better observing conditions. But for many, it also evoked the image of a giant cosmic firework, a unique celebratory gift for America's biggest holiday. Deep Impact was launched on January 12, 2005, aboard a Delta II rocket from Cape Canaveral. However, just one day after leaving Earth, an unexpected incident occurred. The spacecraft's computer system automatically switched to safe mode, an emergency state triggered when a serious fault is detected. Scientists anxiously monitored the data and realized the system was reporting an overheating issue in the thrusters. The entire multi-hundred-million-dollar project stood on the brink of collapse just as it began. Fortunately, after careful analysis, the cause was found. It was merely a programming error. The allowable temperature threshold had been set too low, causing the system to mistakenly believe the engine was overheating. The issue was corrected, and Deep Impact continued its journey as if nothing had happened. Over the next 6 months, the spacecraft patiently traversed 429 million kilometers of space. Along the way, it had to perform 2 trajectory corrections by firing its thrusters. Initially, engineers estimated 3 corrections would be needed, but one maneuver was executed so precisely that the third became unnecessary. This accuracy made the Earth-based control team breathe a sigh of relief and gain greater confidence. On April 25, 2005, Deep Impact's camera first saw Temple 1 from a distance of 130 million kilometers, more than twice the closest distance between Earth and Mars. At such an enormous distance, there was no way for humans to intervene directly. Every control signal took minutes to reach the spacecraft, making real-time adjustments impossible. From this point onward, Deep Impact had to rely entirely on its autonomous navigation system to approach the target. On June 29th, a critical moment arrived. The impactor separated from the flyby spacecraft. From then on, it had to adjust its own course, using its camera to navigate like an autopilot pilot flying straight toward destiny. Scientists chose an approach angle that placed the target surface fully in sunlight so the camera could capture the clearest images while also maximizing the impact velocity. And then the fateful day, July 4th, 2005, came. The 372 kilogram impactor slammed into Temple 1 at a speed of over 37,000 kilometers per hour, many times faster than a bullet. When the collision occurred, the energy released was equivalent to 5 tons of TNT. In an instant, a dazzling explosion erupted, brighter than expected. From the perspective of the flyby spacecraft, it looked like a brilliant cosmic firework display, perfectly suited to the holiday spirit. It was a resounding success, but also left a paradox. Indeed, the impact hit the target perfectly, releasing enormous energy. But the massive cloud of dust it generated obscured the view. For many days afterward, dust and gas continued spewing from the fissure, peaking around 5 days later. This made it difficult for the flyby spacecraft to observe the crater directly as intended. Nevertheless, what was obtained remained priceless, a wealth of spectral data, images, and detailed analyses of the ejected material's composition. Even though the crater was hidden by dust, Deep Impact proved one thing: humanity was fully capable of reaching, impacting, and extracting data from a comet, a success that paved the way for a series of daring missions to follow. The historic impact of Deep Impact not only created a spectacular cosmic firework, but also opened up an unprecedented treasure trove of data about the true nature of comets. Although the flyby spacecraft was obscured by a massive dust cloud, the scientists were not alone. Dozens of ground-based telescopes, from modern instruments like Hubble and Swift to amateur observatories around the world, all simultaneously turned their lenses toward Temple 1. This global observation network made the collision one of the most thoroughly documented astronomical events in the history of comet research. The most important addition came from an unexpected hero: the Stardust spacecraft. Initially, Stardust's mission was to collect dust from Comet Wild 2 and return samples to Earth, completed in 2006. But instead of retiring it, NASA decided to seize the opportunity, redirect Stardust to perform a flyby of Temple 1 to observe the crater left by Deep Impact. In 2011, nearly 6 years after the explosion, Stardust successfully captured valuable images, confirming that the crater was about 150 meters in diameter, much larger than originally estimated. This discovery immediately changed the way scientists viewed comets. Previously, many hypotheses suggested that a comet's core could be as hard as solidified ice rock. But results from Deep Impact and Stardust showed the opposite. Temple 1's surface was extremely porous, softer than fresh snow. Scientists even calculated that up to 75% of the comet's mass was actually empty space, meaning the material was very loosely bound, held together only by weak gravity. In other words, Temple 1 was more like a clump of cosmic dust glued together than a solid rock. This finding was crucial. It explained why, when a comet approached the sun, just a bit of heat was enough to cause ice to vaporize, creating massive jets of gas and dust. At the same time, it reinforced the hypothesis that comets are time capsules, preserving raw material left over from the solar system's infancy, virtually unchanged for billions of years. Spectral analysis of the dust ejected after the impact shed even more light on the story. Scientists discovered many familiar compounds: clays, silicates, sodium, and even carbon-rich organics. These were not signs of life, but they were the fundamental ingredients for life to emerge. The deeper implication was that in the early days, when Earth was still molten and lacking organic compounds, it may have been comets that delivered these precious packages to the blue planet. If true, life on Earth, and perhaps elsewhere, could have originated from these icy, dusty wanderers of the cosmos. The success of Deep Impact did not stop at answering scientific questions. It also opened a new era in how humanity approached small celestial bodies. Previously, we only dared to observe from afar. But from now on, we had proven that we could directly interact and collect data through controlled intervention experiments. This was an important step forward, not only for comet research, but also for the distant future, when humanity may need to confront asteroids that threaten Earth. After completing its primary mission, The Deep Impact flyby spacecraft continued on a new journey named EPOXY, short for Extrasolar Planet Observant Deep Impact Extended Investigation. Starting in 2007, Flyby not only observed other comets, but also contributed to exoplanet research using spectroscopy. Over the next 6 years, it sent back hundreds of thousands of images and valuable data to Earth before officially losing contact in 2013. By then, Deep Impact had left behind a massive scientific legacy. It not only helped humanity better understand the fragile nature of comets, but also clarified the connection between small celestial bodies and the origin of life. Moreover, through its execution and public involvement, the mission became a symbol of the spirit of space exploration. Science was not just for laboratories, but a shared story for all of humanity. Looking back, one can say Deep Impact ended with a perfect chapter. It began with a bold idea, launching a block of metal to crash into a comet, and concluded with a series of discoveries that changed how we understand the universe. Thanks to it, we now know that these icy travelers are not merely symbols of omens, but true treasures containing primordial history and clues to life. And beyond the numbers, Deep Impact left humanity with a lesson. To understand the universe, sometimes we must bravely accept risks, ready to collide head-on with the unknown. It is precisely that spirit which has carried us further on the path of exploration, and which will continue to guide future generations in conquering the mysteries out there. Looking back at the entire journey of Deep Impact, it is hard to believe that what once seemed like a crazy idea, launching a block of metal into a comet, became one of the most important experiments in the history of space exploration. From the moment the spacecraft slammed into Temple 1 to the close-up images of the impact crater sent back years later by Stardust, everything opened up a new picture of the universe we live in. And more importantly, it changed the way humanity sees itself. Tiny creatures, yet courageous and intelligent enough to question the universe and seek answers with their own hands. Deep Impact proved that science is not just dry numbers or lengthy reports. It is a profoundly human journey, a journey of curiosity, of the desire to explore, and of poetic boldness. The 2005 impact was not merely an experiment. It was like a declaration that humanity was ready to step out of its comfort zone to face mysteries with no answers yet. The most miraculous thing Deep Impact brought was not just images of the crater or figures on the mass of dust and water ejected. The greater wonder lay in the fact that from that chaos, science distilled the most intricate fragments of the cosmic puzzle. Organic molecules, clay, silica, things that sound ordinary, became powerful evidence for the hypothesis that life might have originated from wandering blocks of icy dust. In some ways, we can say that Deep Impact helped humanity glimpse its very origins. If comets once delivered the first organic compounds to Earth, then studying them is nothing less than reading the oldest pages of the planet's diary. And this raises a deeper question. If life on Earth began with such gift fragments from comets, then could the universe have sown seeds of life in a similar way on distant worlds? But Deep Impact was not only about scientific value, it also carried a deeply human story. Throughout preparation, execution, and observation, thousands of scientists, engineers, and amateur astronomers all turned toward one common goal. That collision did not just happen in distant space, but also in the hearts of people, where faith in knowledge and the power of cooperation was affirmed. In particular, the participation of countless amateur telescopes turned the event into a global festival. It reminded us that science never belongs only to a small group in laboratories, but is the shared heritage of all humanity. Everyone, whether a professional scientist or someone gazing at the sky through a backyard telescope, could contribute to the larger picture. Interestingly, Deep Impact, though symbolic, also paved the way for a much more practical issue: protecting Earth. In the past, asteroid impacts wiped out entire ecosystems, like the extinction of the dinosaurs 66 million years ago. Today, humanity is no longer powerless before such threats. Missions like Deep Impact and later DART have shown that we can actively alter the orbits of small celestial bodies. If needed, we can turn cosmic rocks from threats into scientific experiments, even opportunities to learn. This is a turning point in the progress of civilization. From being passive before nature, humans are gradually becoming a force capable of shaping their own destiny. And it all started from bold projects like Deep Impact. For thousands of years, people saw comets streaking across the sky and assigned them omens, wars, plagues, or dynastic changes. But today we understand that comets carry no curses, but rather the secrets of life. That change in perception itself is proof of humanity's maturity. From fear, we learn to ask questions, conduct studies, and find answers through reason. The truth is, by understanding comets, we also understand more about ourselves. We realize that life is not a miracle separated from the universe, but an inevitable part of it. The organic compounds on Temple 1 or on countless other comets are the threads linking humanity to the vast cosmos. In 2013, when Deep Impact lost contact, many felt regret. But in fact, that mission never truly ended. The data it left behind is still being analyzed, and new discoveries may continue to emerge for years to come. More importantly, Deep Impact planted a seed of boldness in scientific thought. It proved that sometimes to truly understand the universe, we must step beyond the safe path of observation and dare to attempt what no one has ever done. From Deep Impact, we have DART, the first successful asteroid deflection mission. From Deep Impact, we also gain momentum for future projects such as sampling comets farther away or even bringing materials back for direct study in laboratories. And further still, one day we may use this knowledge to mine asteroids, expanding humanity's presence in the solar system. On a deeper level, Deep Impact poses a philosophical question. Can such small beings as humans leave a mark in the infinite universe? The answer is yes. The 2005 impact, in terms of energy, equaled only a few tons of TNT, insignificant on the cosmic scale, but it carried enormous spiritual value, proof that intelligence can compensate for physical smallness. Humanity does not need muscle, but rather intellect, cooperation, and the will to explore to affirm its place. We can say that Deep Impact was the perfect combination of science and poetry, because every time we touch a celestial body, not only is data returned, but also human imagination, faith, and courage are lifted to new heights. When telling this story to future generations, we can say, there was once a time when humanity sent a small spacecraft to collide with a comet to seek answers to ancient questions, and we found more than expected. Not only organic compounds or porous structures, but also the belief that we can, together, conquer the greatest mysteries of the cosmos. That is the most precious legacy of Deep Impact: inspiration. It carried the message that space exploration is not just for a select few, but the shared story of all humanity. Every generation, when looking up at the sky, has the right and responsibility to continue writing that journey. Deep Impact has ended, but humanity's journey to explore comets and the universe is still only at the opening chapter. We have learned that wandering icy dust blocks are not only beautiful phenomena, but also gateways to the truth about the origin of life. We have proven that human intelligence can turn a bold idea into a great scientific legacy. When you look up at the sky and see a long streak of light across the darkness, remember that it is not just a comet. It is also a reminder that we are part of this vast universe, and that in the long quest for meaning, humanity has never stopped bravely moving forward. Deep Impact may be just a small dot, but it opened an entire new chapter in the infinite book of the universe. And that chapter, we, the curious, the dreamers, and the doers, will continue to write with faith and wisdom.